Okay, so now we move forward to the new material for today, and we're going to talk about the central limit theorem for sample means. It's very important that you understand we're limiting it to the central limit theorem for sample means. The reason is because there are other central limit theorems. We're not going to discuss those. This course focuses only on for sample means. What does it say? The central limit theorem for sample means says that if you repeatedly draw samples of a given size, such as repeatedly rolling 10 dice, and then calculate the means of those samples, those means tend to follow a normal distribution, a sampling distribution. As sample size increases, the distribution of means more and more closely resembles that normal curve, that normal distribution. The normal distribution has the same mean as the original distribution, and the variance that equals the original variance divided by the sample size. So standard deviation is the square root of variance. So the standard deviation of the sampling distribution is the standard deviation of the original distribution divided by the square root of the number of, in this sample, in this case n. The variable n is the number of values that are averaged together. So this is how we express with our normal distribution notation that we're doing a central limit theorem for sample means normal distribution, not a regular normal distribution. First, we start with x bar instead of x because we're not looking at a particular score. We're looking at a means. And then n for normal, the first place is always for the mean. In this case, it'll be the mean of the sample. They're the same. But then for standard deviation, it's the standard deviation, but then you must divide by the square root of n. That's sampling error. Okay. So, without any further ado, I want to show you a quick video that basically says where this all comes from, what's important, gives you a little background of it. Okay? Here we go.
Even if you're not normal, the average is normal. Hello, I'm Josh Starmer and welcome to StatQuest. Today we're going to talk. And the good news is that it's a pretty simple concept. In this StatQuest, I'll explain what the central limit theorem is and why it's important. Like most things in statistics, I think the central limit theorem is easiest to understand if we look at some examples. So let's start with a uniform distribution. This one goes from 0 to 1. It's called the uniform distribution because there is an equal probability of selecting values between 0 and 1. The probabilities are all equal and thus are uniform. We can collect 20 random samples from this uniform distribution and then calculate the mean of the samples. And on the right, we can draw a histogram of the mean value. Since we only have one mean value, the histogram isn't very interesting. But after we collect 10 more samples and collect 10 more means, the histogram starts to look a little more interesting. Here's the histogram after collecting 20 samples and calculating 20 means. 30 means, 40 means, 50 means, 60 means, 70 means, 80 means, 90 means, and 100 means. After adding 100 means to the histogram, it's pretty easy to see that these means are normally distributed. However, to make it easy to see that the means are normally distributed, we can overlay a normal distribution. You might have noticed that in the last two slides, I put means are normally distributed in bold. I did this because this is what the central limit theorem is all about. Even though these means were calculated using data from a uniform distribution, the means themselves are not uniformly distributed. Instead, the means are normally distributed. Bam! Here's another example. This time, we'll start with an exponential distribution. Just like before, we can collect 20 random samples from this exponential distribution. And just like before, we can calculate the mean of the 20 samples. And lastly, we can draw a histogram of that mean over here on the right. After we collect 10 samples and calculate 10 means, the histogram starts to look a little more interesting. Here's the histogram after 20 means, 30 means, 40 means, 50 means, 60 means, 70 means, 80 means, 90 means, and 100 means. After adding 100 means to the histogram, we can see that they are normally distributed. Even though these means were calculated using data from an exponential distribution, the means themselves are not exponentially distributed. Instead, the means are normally distributed. Bam! So far, we have seen that the means calculated from samples taken from a uniform distribution are normally distributed, and means calculated from samples taken from an exponential distribution are also normally distributed. Well, it turns out that it doesn't matter what distribution you start with. If you collect samples from those distributions, the means will be normally distributed. Yes. Who cares? The sample means will be normally distributed.
That's big. Whatever you start with, you can use this formula.
Because the sample means are normally distributed, we don't need to worry too much about the distribution that the samples came from. We can use the means normal distribution to make confidence intervals, do t-tests where we ask if there's a difference between the means from two samples, and ANOVA, where we ask if there is a difference among the means from 3 or more samples.
This we do later in the
pretty
course.
Much any statistical test that uses the sample mean.
Okay, so that's the main point of what it is that we have going on here. That when we apply the central limits theorem, it doesn't really matter what we start with. It always works for the means. So that's a really big conclusion. And the second thing is that a little later in the course, we're going to get into t-tests and so on and so forth. And this theorem will be used for that. So what you should walk away from this video, clearly explaining video, is that no matter what you start with, central limit theorem is going to work. And that once you apply it, it has applications in many different areas. Okay, now the next we'll get into how to apply it.